Hello, I'm Chris Beal, CEO of Nextdoor, and today we'll be going over a real-world case study of a sensor-based bulk sorting system which was installed in 2019 and which used the magnetic resonance technology for sensing, which is supplied by Nextdoor. So in this video, what you're looking at is the discharge end of the bulk ore sorting plant itself. And a pneumatically actuated flop gate diverter is directing material either to an upgrade or to a reject pile on the basis of measurements that are being produced upstream on the conveyor belt by a magnetic resonance analyzer, which is tuned for copper as chalcopyrite and generating measurements every 2 seconds. So this presentation is going to go over the setup of the bulk ore sorting plant itself and also how it integrates with the mining operation. And then we're going to end up at the results that were demonstrated from this trial. And one point in particular, which we have found to be one of the biggest value drivers for mining companies in their adoption of this technology, which is the demonstrated capability of bulk ore sorting to generate an improved overall recovery of metal, in spite of the fact that at the bulk ore sorting stage itself, you may incur some metal losses. So this is the Cozamin mine. It's located in Zacatecas, Mexico, and it's owned by the Capstone Mining Corporation, which is a TSX-listed Canadian mining company. It is an underground mine, and they use the long-hole open stoping mining method. The mine produces commodities of copper, zinc, lead, silver, and gold, although the primary commodities are copper, zinc, and silver. And in 2019, the mine produced 1.15 million tons of ore, with an average head grade to the processing plant of 1.5% copper and 1.07% zinc. And here you see the ore body itself underground. This is a polymetallic massive sulfide ore body, and it is separated into some distinct zones, which we benefited from for the purpose of this bulk sorting plant. Now, the MNFW zone, which is the dominant ore source for the processing plant, is a copper-dominant area of the mine. And this differs from the other areas of the mine where you have copper and zinc together. So the MNFW Z zone is copper dominant, and the copper mineralogy of it is almost exclusively, or to the extent that anybody can tell, exclusively chalcopyrite. And that's incredibly well suited to the MR sensing technology. The materials handling chain looks like this. Material is drawn from a stope firing or development heading firing and loaded directly onto trucks, bypassing a stockpile to reduce mixing to the extent that's possible, or would typically be hauled to a series of ore passes underground, crushed, and then hoisted to surface using 2 5-ton skips. But during this bulk sorting trial, the material was predominantly trucked directly from the heading up the decline and to a dedicated ROM pad on surface. Once it was dumped on the ROM pad, material was loaded by front-end loader to a crusher at the front of the bulk sorting plant itself, which is shown here. So those people who are familiar with particle and bulk sorting systems will immediately see possibly the biggest advantage of bulk sorting systems, which is how straightforward and simple they are. In this case, you have a crusher, a conveyor belt, a sensor, and a diverter at the core of this system. And we'll go through these individual components, but in particular, for the Nextdoor sensing technology, we have further advantages over other bulk sorting systems, which is that, number one, the ability to measure very quickly means that your pod sizes are smaller and the length of conveyor belt that's needed after the analyzer itself can be much shorter, making the system more compact. And then secondly, the MR technology is a deeply penetrating sensor technology. And so the crushing that's required ahead of the sorting system itself, whereas ahead of the sensor, can be pretty light, and you can sense through very coarse material. So going from right to left in this photo, you're looking at a hopper feeder. There's a scalping screen at C. That material bypasses directly to the feeder belt, and the coarse, oversized material is crushed in B, loaded onto the main conveyor, Between E and F, there is a weightometer reading gross tonnage of the material. F is the magnetic resonance sensor, which is installed around the conveyor belt itself, and that's connected by cabling to G, which is the magnetic resonance electronics, and that system directs the diverter gate downstream, denoted with an H, as to whether to upgrade or reject the material, and then that is collected by front-end loader again. Like I said, one of the advantages of the magnetic resonance technology is the deeply penetrating nature of it. So the technique measures the entire sample volume, and that is regardless of how coarse the material is or fine the material is. So the top size of the material that was going onto the main conveyor in this case was 180 millimeters, although I think that we actually exceeded that and went up to about 200 millimeters at points. And that goes all the way down to the fine size. And the MR analyzer is capable of detecting all of that. Here you can see a photo of the MR analyzer installed on the conveyor belt. So after installation and commissioning, you would typically do a series of tests to make sure that the analyzer is working and is producing accurate measurements, and that's what's shown here. Bulk samples between 50 and 100 kilograms were loaded into the sensor volume, measured, and then a blind assessment was done where that material was then shipped off to the laboratory on site, where it was crushed, homogenized, subsampled, and then assayed. And as you can see from that chart on the right, the laboratory assay total copper lined up quite nicely with the measurements being produced by the MR analyzer. And it's important to note here that one of the distinct advantages of the MR technology is the reliability of the system. And the reason for that is that you don't need to recalibrate the analyzer at any point during its operation. It's a factory calibrated system, and it doesn't matter if you have changing host rocks, changing moisture levels, penalty elements or chemicals that are present either in the conveyor belt or the material itself. The measurements will continue to be produced accurately. We have never had an analyzer that's operated in the field that needs to be recalibrated. So the actual results of the sorting project itself. As you can see from the table, the sensing interval was 2 or 4 seconds. Ultimately, we went with a 2-second measurement interval. And the measurement precision, or the 1 sigma repeatability of the measurements, in this case was plus or minus 0.023% in that 2-second measurement interval. The feed rate of the plant overall was 199 tons per hour, but notably, this is using a conveyor belt speed of 0.62 meters per second, very slow. You could quite easily double or triple the speed of that conveyor belt, and as a result have a throughput for the plant of 400 or 600 tons per hour. The pod size, which corresponded to the feed rate shown there, and the 2-second measurement interval was between 50 and 150 kilograms. So that is the resolution of the separation of the material. The total feed, 1,660 tons, and we won't go through all of this, but the important parts here are that the average feed grade was 1.1% copper to the process, or to the bulk ore sorting plant for the duration of the trial, and the average upgrade, or upgraded grade, was 1.43% copper, a roughly 30% improvement in the copper grade of the material. About 30% or 32% of the material was rejected, an average grade of 0.4%. Again, this shows how high grade this operation is. And notably, there's no optimization in the result that was delivered here. By that, I mean that diverter cutoff grades weren't calculated on an economic basis for this mine. There was a range that was applied to selectively test different configurations. So cutoff grades range from 0.2% to 1% copper for the trial. Overall, this result represented an 88% copper recovery of the sorting stage. But in spite of that, and this is something that we need to explore, the net recovery improvement of 6 to 8% was demonstrated at this project. And we'll go into how that is achieved. This concept has been explored by a number of other people, a number of professionals in the pre-concentration space. In particular, a couple of papers that I quite like, produced by the team who are now at Hatch, Duffy, Valerie, and Holtham. and 2 papers of theirs. So the AusIMM 2015 white paper about bulk ore sorting, which explored this recovery improvement for a conceptual mine, open cut mine, and then they went in and again applied the same concept in a more specific case study for the PUCAM operation in 2016. Now this is one aspect of many that are explored in these papers, but the important aspect that we'll be focusing on is that by changing your mining operation a little bit, by tweaking the cutoff grade, what you can do is you can actually improve the recovery from the mining operation in a way that more than offsets any potential losses that you incur in the bulk sorting stage itself. You can do that consistently, and it provides a rather significant increase to your metal production. So what does this look like using the actual data that was produced from the bulk sorting plant in this case? What you're looking at here on the left-hand side is a histogram of every measurement was taken during the 6-month trial. This is a little under 28,000 measurements. And what we can do here is we can calculate a sorting recovery curve. So by applying a change in cutoff grade over this histogram, we can calculate the metal recovery above the line and the weight retained above the line, and then plot it on this chart on the right-hand side. So this looks something like this. With these sorting recovery curves, the intention is that you want to be in the top left quadrant of this chart. And in that you would be in a position to have a high recovery and you'd have a low weight retained, or you would have most of your material rejected, or a higher proportion. So what's shown here is that curve again, and the dot that's shown on that curve is the actual result that was achieved during this trial, and then the rest of that red curve is a theoretical result which can be calculated from the measurements that were produced. So what we can do to demonstrate the net recovery improvement is to use the conventional geological grade estimates, which were assigned to the same trucks that were delivered during this sorting trial. And that's shown here. So these red bars represent the grade estimates which were assigned to each of the trucks depending on where they were coming from in the mine. And as you can see, they aren't as spread out because it's not a continuous measurement. It's an estimate that's produced by the geos on site. But what we can do is we can calculate an analogous curve and plot it against the bulk sorting curve that we've got shown on the right-hand side there, which looks like this. So there's groups who've discussed the fact that bulk ore sorting in some ways can be considered an extension of conventional geological grade control, and that's really shown here. What you're able to do is, because you have a much better quality of data and much higher resolution, you're able to improve on the results that would otherwise be achieved by simply assigning the destination of a truck as to whether it goes to a waste pad or to a ROM pad based on the measurements that you can produce from the bulk ore sorting plant. So the actual result, that dot shown here, represents a 6.3% improvement in copper recovery within the same ore that was delivered from the mining side and the same quantity of ore that would then head on to the processing plant. And you can do this at any point along this curve to compare what your recovery would be if you use conventional geological control and what it would be using a bulk sorting system. So this gives you your 6 to roughly 8% recovery improvement. So how is this achieved specifically? To explore this, we'll take a look at 2 different scales of grade variability. Number 1, at the macro scale on a truck-by-truck basis, and then number 2, within the trucks themselves. So on the left-hand side here, you're looking at a chart. Each one of these blue dots represents a single truck. On the x-axis, you have the grade estimates that's produced by the on-site geo. And then on the y-axis, you have the grade measurements which are produced from the MR analyzer itself. And as you can see, there's a broad distribution of that. The material in these trucks is frequently, and this is something that we've seen across multiple ore bodies in multiple operations, there are frequent misassignments that occur. So either your waste is being misassigned as ore and going to the processing plant, or much worse, your ore is being called waste and sent to the dump, and you incur losses from your mining stage there. So you're mining all of this material, and without very good data, you're unable to make accurate assignments of it to the right location. So that's the macro scale. On the micro scale, within a single truck, you can see here on the right-hand side, this is a histogram of all of the pods within one truck. So the average grade was 0.73% copper, but you can see there's a broad distribution of low and high grade within that, and you would be able, using bulk sorting, to separate those low grade pods from that and then send on a higher grade result to the processing facility. So that's effectively what we're doing. By using bulk ore sorting, you're generating much better data and much higher resolution data on the material that you're already mining. So if you were to have a fixed constraint on your mining capability, the tonnage that can be produced from the mine, we've shown here that you can generate a consistent net recovery improvement. Again, this is in spite of the losses that you might be incurring at the actual bulk sorting stage itself. There's an extension of this as well, which wasn't explored during this project, but if you were then to drop your cutoff grade, and that material, which might be marginal or might be geologically risky, could be sent to the bulk ore sorting plant, what you can do is you can even further increase that mining recovery and generate a much better result than what we've shown here. So there's a lot of scope to extend this positive result that we've explored here at other operations as well. And that's it. Thank you very much. My name is Chris Beal. Have a good day.